Yeah, so thank you for inviting me here. My name is Sylwia, and today I will say a few words about the method that we are developing at Nicolaus Copernicus University. It is called Fourier-domain quantum, optical coherence tomography. I am responsible mostly for the experimental part, and my collaborators, Krislani De Brito and Piotr Kolenderski, are the theoretical part. Okay, so I'm partially at Nicolaus Copernicus University in Toronto, but for most of the year, every year, I can be found in New Zealand. So it is the country with 2 islands that can be found close to Australia, and Christchurch is on the better South Island. Okay, why quantum optical coherence tomography? It is because the quantum version of OCT gives us 2 times higher axial resolution with the same bandwidth, and the chromatic dispersion is cancelled. It means that the effects that degrade the axial resolution in OCT are not present. And why is it important? Why these 2 features are so sought after? Yeah, it is because the axial resolution in OCT scales with the bandwidth. So let's assume we have light whose wavelength starts at 450 nanometers, and then on the axis scale we will have the wavelength range. So this is how the axial resolution will change. We see it's not linear. Actually, this is the equation governing the change of the axial resolution as a function of the wavelength range. So to get 1 micrometer axial resolution, we need a bandwidth of 110 nanometers. To get an axial resolution that is twice better, so 0.5 micrometers, yeah, we need 290 nanometers, and then 0.25 micrometer means that yeah, the bandwidth should be basically ridiculous, 1700 nanometers. So yeah, that's one of the problems. The other problem is the chromatic dispersion. So assuming that we have only a piece of glass in the setup, which is 1 millimeter thick, with relatively low group velocity dispersion, the axial resolution, okay, first it improves with the wavelength range, but then we can see it actually decreases. And it was established that the practical limit here is around 1 micrometer, and that resolution was already achieved a long time ago, so it was 2002. So basically at the very beginning of optical coherence tomography as a method. Okay, another problem with chromatic dispersion is that it is everywhere. It can be in the interferometer, so in the setup itself, but the objects that we image, they are dispersive as well. For example, the most popular object that is imaged with OCT, so the eye, is very dispersive. Even the retina itself, so here you can see the retina. So, because this object is inherently dispersive, we can either compensate the effects of chromatic dispersion on the like most superficial layers, so we are able to get a sharp image of the front of the object, but then we lose information at depth, or we can focus on compensating chromatic dispersion at depth, but then the front is not sharp. So that's the main problem in OCT, and that's why quantum optical coherence tomography is very, I would say, attractive, because that limitation is not present. You actually don't have to worry about dispersion when constructing the setup and then when imaging the object. Of course, quantum optical coherence tomography, quantum OCT, removes even order dispersion, chromatic dispersion, which means that the third order dispersion remains, but the contribution of that type of dispersion is negligible, and we don't have to worry about. So that is why. Quantum OCT balances resolution improvement and nonlinearities, so the effects of chromatic dispersion. Quantum OCT looks a bit different than traditional OCT. We have a light source and an interferometer as well, but in quantum version, we have a source producing entangled photon pairs, then an interferometer that in classical terms we would, it is called a Hongo-Mandel interferometer, but if we were to describe it in classical terms, that would be a Mach-Zehnder interferometer, and then we have a coincidence detection. The state of the art in quantum OCT is the time domain detection.
So just for pedagogical purposes for students, could you use this scheme to explain this standard optical coherence tomography scheme? Without quantum, just what would be like this?
Okay, yeah.
So it's not obvious for most of the people.
Mm-hmm. Yeah, so there are three main parts in every type of OCT. So we have a light source. In conventional OCT, it is just a spectrally broadband laser. In quantum OCT, it is a bit more complicated because we have to generate photon pairs. Then the light goes into an interferometer. So that is actually the part that might be exactly the same for both. And of course, the detection. In conventional OCT, the most popular type of OCT, you will have a spectrometer. So a diffraction grating for dispersing the light and a line scan camera to detect a spectrum. In quantum optical coherence tomography, because we have two photons, the detection is a bit more complicated. We have two detectors which detect the coincidence, so the simultaneous arrival of the photons at each detector.
Okay, and when you describe this axial resolution plots for this classical scheme, yes? So I understand this axial means the resolution in terms of depth. Yes, I mean axial means with respect to the depth of the sample. Yes. So
depth. Yeah. So along the propagation path of the light inside the sample. Mm-hmm. Yes. So as I said, we have two single photon sensitive detectors. And we measure the coincidences, so simultaneous arrival of photons at each. As a result, we get a dip, I will call the signal that we get in time domain, quantum OCT, a time domain A-scan. A-scan is a term from OCT, but also from ultrasound. So this is the signal that describes what the object looks like depth-wise. A-scan. We can observe if we have a mirror as an object in the interferometer. We observe that at certain time delays, there is a dip. So this dip appears because the coincidence rate drops when the position of the mirror in the reference arm matches the position of the mirror in the object arm of the interferometer. So basically, close to the 0 time delay, we observe the drop in coincidences, so we observe a dip. And right now, if we imagine, so the axial resolution would be defined as the full width at half maximum of the dip. So we can imagine that, for example, we have a piece of glass, so 2 interfaces. Then we would observe 2 dips while we scan the mirror. It's not as simple as that. In quantum OCT, we have a dip corresponding to one interface, the other dip corresponding to the other interface in the glass, but also there is another element in the A-scan that's an artifact, and that is one of the shortcomings of quantum OCT, quite unresolved yet. The main issues with the time domain approach is that the acquisition times are quite long, and that time scales with the axial resolution. This is because if the axial resolution is better, then you need more data points to sample that dip, right? And of course, it will be even longer with thicker objects because you have to scan, you have to reveal the whole object, right? And also the problem with the fact that the reference mirror has to be scanned. So in general, the measurement can take hours for thicker objects, such as pieces of glass. So we propose to perform detection in the Fourier-domain. And we showed...
These detectors are not spatial resolving, they're just...
Here they are single pixel
So if I want
detectors.
to scan an object in the other direction, I have to just move everything, yes? Sideways.
To create a two-dimensional image, normally you just scan the object, right? You move the object with respect to the beam, or beam with respect to the object, yes. So with the Fourier-domain approach, we are able to reduce hours to minutes, and I will quickly show you how we did it. Okay, so in the Fourier-domain approach, we still have, of course, single photon detectors, but we also have a dispersive elements, so that the coincidences that we measure, they are discriminated by wavelength. So as a result, we obtain a joint spectrum, which can be recalculated to an A-scan using two-dimensional Fourier transformation.
Then you don't need to displace the reference mirror.
Yes, the reference mirror position is fixed.
But this is also how it's done in this classical OCT? That you do this, because you mentioned you do spectrometry, yes? Spectrometry.
Yes, yeah.
How
So
does it differ from the standard classical?
like the main difference is that the simply a laser light is used So we have a lot of light to spare, if I can say it like that, and the spectrum is one-dimensional. And this is basically enough to calculate an A-scan. So in traditional OCT, we detect a spectrum, and then we Fourier transform it. It is one-dimensional Fourier transformation into an A-scan.
This is a joint spectrum of photon bursts, Rafał.
Yeah.
Mm-hmm. Yes, and yeah, as a fun fact, in OCT, traditional OCT, there is a time domain OCT and a Fourier domain OCT. So OCT in general gained popularity, and it became very popular because of the transition from the time domain to the Fourier domain. Because with Fourier domain, people were able to perform OCT very, very fast. Right now, with this approach, OCT is able to produce three-dimensional images in real time. So yeah, basically what we did, we learned the lesson from traditional OCT. We noticed that, okay, for quantum OCT, we only have this time domain detection. Let's try Fourier domain detection and see if we can provide at least a fraction of the revolution that happened in traditional OCT. So, okay, hours to minutes. So that's a good step forward, I think. Okay, so Fourier domain versus time domain. This is the coincidence probability density describing, it's like a point, starting point for both domains, for the signals in both domains. But in the time domain signal, of course, we have to perform this summation, this integral, right? And in the Fourier domain, we we don't do that, right? So we have more information, but I would say it's a different representation of the same information. So in both equations, we can see the terms responsible for the structure and the terms responsible for the appearance of artifacts. I put something like that here because in the Fourier domain, actually this term produces another artifact. So I don't know if I show here. No, I don't. Whereas in time domain, quantum OCT, we have one artifact per interface pair. In Fourier domain, quantum OCT, we will have two artifacts per two interfaces. Okay, so this is a mirror as an object. We have an interference pattern, just one frequency on the joint spectrum. Fourier transformation will give us this symmetrical image. So we can look basically at only half of it. Because yeah, the other half is exactly the same thing as the first half, and by taking the diagonal, we get an A-scan. For two interfaces, so for example, for an object that is a piece of glass, the joint spectrum will have a more complicated pattern. Two-dimensional Fourier transformation will be more complicated as well. We can observe on the diagonal, we will have the structure, and the off-diagonal elements will be the artifacts. And of course, on the other side here, we will have, the same thing will be repeated as on this quarter, maybe. And we can see traces of the artifacts here is because they overlap at the diagonal. And as I said, two types of artifacts. One that I call a midpoint artifact. It will appear exactly in the middle between the interfaces. and the other artifact will appear at the distance from 0 that is equal to the thickness of, or half the thickness of the object. Yeah, so when I zoom, you can see the traces of the artifacts. But yeah, the good thing for Fourier-domain quantumosity is that we have a way to identify them, right? Of diagonal elements artifacts, diagonal elements the structure, right? So, and they have this behavior. So the thicker the object, the better the separation of the artifacts. So we can see that the midpoint artifacts, they are separated so that we cannot see any traces in the A-scan. Also, the thicker the anti-diagonal width of the joint spectrum, the better the separation. And this is because the width of that element in this direction, right? And anti-diagonal direction scales with the width of the input signal input spectrum. So to increase this anti-diagonal width, one needs to use the pump, so the laser that is used to generate photon pairs. That is spectrally broadband. And of course, there are restrictions for the crystal because the crystal has to allow that anti-diagonally broadband emission, if I could say it like that. I will show later that, yeah, so these are simulations, and this thickness is exaggerated a bit. In reality, this anti-diagonal width is quite small. Okay, New Zealand. Auckland is the biggest city in New Zealand if anyone would like to come visit. So this is where most of the planes land. This is the biggest city, biggest than the capital of New Zealand, so Wellington. And to encourage you to come and visit, I present my photos. So these are not from the internet. I actually saw the things that you can see here. So this is reality, guys. So this is the Auckland skyline, early in the morning. Then, okay, as a proof that I was there, this is me. The biggest building in Auckland. It's called a Sky Tower with a magnificent view over the entire area, including the Gulf here and the adjacent islands. And this is taken from a volcano called Mount Eden. There are a lot of volcanoes, dormant, no, not dormant, dead, extinct. So you don't have to worry about them. You can go up each and safely look at the views. Yes, but Auckland is on the North Island. Your destination should be the South Island. Christchurch is here, so this is where my university is and where I am employed. So this is a good starting point for a big adventure in New Zealand. Here you can see this nasty bird. So if you decide to come and you are in this place called Arthur's Pass, avoid it. It might look friendly, but no, it can destroy your car and can destroy your shoes.
Is it TV?
Oh, no. Kia, yes. Oh, great. But yeah, you can see really breathtaking views. This is my photo. The previous ones were taken by my husband. That's why they are much better. But yeah, these are actually the views that you can expect. Yeah, but the real, I would say, money maker for New Zealand is Queenstown. This is the place to be when you are on the vacation. And as you can see, it's worth it. Again, me. You can see that for my trips I use the same jacket, so that's how you will recognize me on the photos. And Milford Sound. Okay, let's go back to science. Yeah, so we set up the experiment in the Institute of Physics. The source producing photon pairs, the schematics of it looks like that. We have the pump light, which is a pulsed laser, 775 nanometers. It illuminates a nonlinear crystal, and this crystal produces the photon pairs at 1550 nanometers. They are separated, and each photon goes to a separate arm. So basically, the interferometer starts at the crystal. In the interferometer, okay, we have a reference arm and the object arm where the object is placed. And all this polarization optics is to ensure that maximum light returns and is returns from the object and is detected. And here in the reference arm, so that the fringe visibility, so that modulatory pattern is maximum. The visibility is maximum. The Fourier-domain detection, so as a dispersive element, we use a fiber spool in each channel for each photon, and a single pixel detector to detect the photons. Yeah, because the fiber spools, these fibers are really long, 5 kilometers each. There is a lot of dispersion that delays certain wavelengths differently. That's why the spectrum is detected in time. Okay, so the experimental data, the result, the detected raw joint spectrum is far from perfection. First, we can see some noise that is most probably from the pump, but we are not sure yet. Also, the joint spectrum itself, right? It is bent a little. This is due to the dispersion of the fiber spools. So on one hand, fiber spools, they enable us to see the joint spectrum, but also they introduce these effects that need to be mitigated. So a two-dimension.
The detected here is actually the time.
Yes, and that time is
The wavelength.
True. Yes.
And then, because you could back that out, yes, what you just described, or not, the nonlinear dispersion of the fiber.
Yeah. So in the okay. We can talk about it later.
Yeah.
Okay. Yeah. Okay. All right. Okay. So two-dimensional Fourier transform will look quite ugly because of that. Yeah, we can compensate for fiber dispersion, and then we can go back to the right shape, and then the elements in the Fourier transform start to look decent. We can see this element that is represents the structure, so the mirror that was imaged. And here you can see that because the diagonal width is so big, the width in the Fourier transform is small. And on the other hand, the anti-diagonal width is quite small. So the width of this element in this direction will be quite big, and that's why we expect to have problems with the artifacts as well. These are the widths in nanometers. And okay, we can rotate the joint spectrum so that the interpretation is easier, and then the interpretation of the Fourier transforms is easier as well, because then the diagonal direction will be on the x-axis and the anti-diagonal direction on the y-axis. Yeah, so let's use these two. Okay, by changing the time delay in the interferometer, so basically shortening or extending the reference arm length, we can acquire these different joint spectra, and we calculate them to A-scans. And when we plot these A-scans, we can estimate the imaging range, so the maximum depth that we are able to visualize with quantum OCT, and also how the axial resolution changes with depth. So here you can see that we have this sensitivity drop, and the imaging range that is defined as a 6 dB drop is at 0.34. This is the definition of the practical imaging range. So one would expect to only visualize objects that are this thick with good fidelity, with good visibility in the A-scan. And this drop is due to the limited spectral resolution of the detection. This is exactly the same effect that is observed in traditional OCT. We can see that at the depth, the axial resolution drops, which is again connected to this sensitivity drop. We were, of course, yeah, we have the capability.
Is it really sensitivity drop or width of those peaks?
Yeah, the width of the peaks, because of the limited.
Because the resolution should be how I would expect the width of the line width.
Yeah, but as far as I remember, the source is similar for that drop and for the drop in the axial resolution. Yeah. Okay, so we can manipulate the length of the reference arm, right? So we are able to also detect the time domain quantum OCT and compare. So we have a similar axial resolution like for both approaches. When we apply conventional OCT, so that will be the same interferometer, but instead of the quantum light, we will use traditional laser whose spectral parameters are similar. We can see that the resolution is worse, just as we expected. Yes, it's in the case of conventional OCT, it's not exactly twice worse, and that is because the width of the quantum OCT spectrum, so the diagonal width, is slightly bigger than the full width of half maximum of the conventional OCT, so the light source used in the conventional OCT. But yeah, you can see that effect. Okay, so let's look at more complicated objects. So in this case, a thin glass, a joint spectrum starts to look more complicated. Two-dimensional Fourier transform as well. We can see 1 and 2. This is the structure, so the first interface, the second interface of the glass, and A, B, and it's like mirror image. These are the artifacts, and they are far away from, maybe not that far, but they are not at the diagonal. That's why we know they are artifacts. They are very close to the diagonal, actually. That's why when we extract the A-scan, we can see their traces, and they are quite pronounced. When we compare to the time domain signal, time domain A-scan, we see just one artifact. Like I told you, there's only one artifact for the time domain approach. And yeah, when we compare to the conventional OCT A-scan, we have two interfaces, but also we have this peak, which we call the autocorrelation peak. It's basically a peak type of peak that appears because the light reflected from the interfaces interferes. So it will be positioned at the distance from 0 that is equal to the thickness of the glass, right? Then a slightly thicker object, plastic. Yeah, we can see that because it's thicker, the artifacts moved apart a bit. Still, we can see the traces of them, slight traces. Okay, the scan that I did here was very coarse, and you can see it on the with the orange line, and you can see this one of the artifacts that is not compensated, not reduced. But a quicker scan shows only the dips corresponding to the interfaces. We cannot see the artifacts, which is most probably due to the fact that that artifact is really small, and we have lower sensitivity, so bigger noise for shorter acquisition times. Yeah, for conventional OCT, again, clear two peaks and the autocorrelation peak. Then, yeah, I wanted to show this to you because this image you can interpret as a kind of B-scan, so a two-dimensional image. What I did here is that I moved the reference arm stage, so the length of the reference arm was decreased, and because of that, like artificially, the position of the object moved. So you can interpret this image as an image of a glass at an angle, and this would serve as a simulation of what to expect if we would would like to have images from quantum OCT. So you can see that, okay, you have these elements that would correspond to the object, right, 1 and 2, but also a small trace of an artifact, the midpoint artifact, right, always in the middle between the interfaces, but also this other artifact here. So it's hard to interpret such an image, but it's easy, right? Because we have the object is not complicated, just two interfaces. Let's look at a more complicated object then, two thin glasses, right? So two-dimensional Fourier transform is very hard to interpret. Still, you can see some elements. The Fourier-domain A scan, well, you can, after some detective work, you can identify the interfaces, right? This is easier with the time domain approach, but still we have these uncompensated, unreduced artifacts. For conventional OCT, it's actually not a problem. We just have to make sure that our image, the actual image, doesn't overlap the autocorrelation peaks. Yes, but if we were to sort of simulate how these two thin glasses would look at an angle, if they are put at an angle and scanned, yeah, it's a mess. The artifacts, they scramble the image completely. So, lastly, I would like to summarize the acquisition times, mostly for time domain quantum OCT, so the current state of the art, and Fourier domain quantum OCT, so what we proposed, and contrast this with traditional OCT. So you can see that the improvement is quite substantial, especially for thicker objects. This is because in Fourier domain, QOCT, the mirror is fixed, and you just have to make sure that the measurement time is enough to capture all the details in the joint spectrum, right? You don't have to scan, you don't have to spend the time to scan the object, to scan the object in depth. Yeah, so if you would like to know more details, then you can look at our manuscript, which is available on archive. And also, as a reminder, New Zealand is a very beautiful country. Waterfalls, different kinds, accessible. These very, very interesting phenomena, so extremely still water, or this very picturesque fog. Again, Milford Sound, that's the place to be, next to Queenstown. And in conclusion, Fourier-domain quantum OCT gives us high resolution, short measurement times, but still we have artifacts. So that's right now a big deal breaker for this kind of approach, but we have a way to identify the artifacts. And maybe with these advanced computational tools like machine learning, we could get rid of them completely. Of course, it is still a long way from traditional OCT, especially when it comes to imaging biological objects. So biological objects right now are out of reach for quantum OCT. And I would like to thank my collaborators and my funding agency, and thank you.
Thank you very much. Questions?
So maybe I didn't quite catch that, but what is the wavelength in nanometers that is on the plots that you were showing?
1550.
It's 1550.
Mm-hmm. Yes.
So the dispersion is of 5 kilometers is like 100.
Oh, you would like to have a number? I don't have it with me.
Okay, but it's the telecom dispersion. Okay, thank you.
It's enough to.
Or the resolution that you
to
have.
have a good spectral resolution.
So what is the resolution that you have in frequency?
Yeah, I don't have that number either, but
okay, we can talk later.
A spectral resolution that is enough to give us the imaging range of 0.34 millimeters.
Okay, and the range of wavelengths, so the spectral bandwidth on those plots?
Oh, that's a nice question, because here the spectral width is 75 nanometers, but actually the full spectrum is much wider, but we are not able to capture it because the pump that we use is a pulsed laser, 80 megahertz. And yeah, we are only able to catch the spectrum in 12.5 seconds because of that.
You
so we're not able to catch the whole
pulses.
spectrum.
Yeah, sure. Okay.
Yeah,
okay.
right now I'm working with the pulse picker,
so this
and
is
we will be able
broadband.
to show the full spectrum, yes.
Okay,
So
okay, thank you.
I can only say that I did that experiment a long time ago with the same, more or less tools, same light source. And back then, I was able to get the axial resolution of 5 micrometers. Right now, I can only get 11, right? So it's much broader in reality.
Thank you.
Mm-hmm.
If I may ask, what is the bandwidth of the pump lasers that pumps the nonlinear medium? These are
it's around 8 nanometers at 775.
Thank you.
Mm-hmm.
More questions?
So maybe you could just comment, because you mentioned that this quantum has 2 times improvement, yes, compared to classical. So it's because of, intuitively you can explain it how? Because of visibility of Hongo-Mandel deep or something else? And is it really fundamental or just for 2 photon sources?
I think it's fundamental. It's the way it's what the entangled photon pairs are really. We can go back to the equations, but it's a long way from this this slide.
But
I
if
can
we
find it.
if we have like more complicated entangled states of more photons,
Then the
could we do
resolution.
better?
Yes.
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 No,
Is
but
there-
I was just asking how fundamental is this statement. So is it just 2 photons? Yes.
Yes, with 2 photons you have twofold resolution improvement. With 3 photons entangled, you would have 3 times. Yes, this is how it works.
Yeah, so maybe that's related to the question that I wanted to ask. What would happen if you would put there like a 2-mode squeeze vacuum instead of like those just 2 photons? Yeah, would it improve this scheme or not?
I think this research was already done, and I think it was done in the group of Maria Czekova. I don't know if you know her. I don't know details, but yeah, they were able to obtain resolution improvement, but the quality was worse because here we work with Gaussian peaks, and like fundamentally, I think the peaks they are the quality and the shape are not good for imaging. So as far as I remember, the problem was with the quality of the images, but yes, they were able to obtain A scans as well. I can point to the right literature later, if you like.
More questions or comments? If not, let us thank Sylwia once again.